was saved. Well, we'll see. If it wasn't saved, then you just missed the first, I don't know, 30 minutes or so of the lab. All right, so let's continue on here. This is a lab station here, basically where you can do your work. There's an electrical outlet there. And then we have 3 taps here. One tap is for VAC. VAC stands for vacuum. So this is low pressure in here. And so you can feel it's sucking. It's not a very strong vacuum. But sometimes we need vacuum where we can suck gases out or air. This is high pressure air. That's off right now. Air pump must be off. But we have compressed air in this tap. And this tap here is natural gas. Our natural gas is attached to a Bunsen burner here. This is a Bunsen, or actually, this is a fancy Bunsen burner. And this fancy Bunsen burner, they call a Tyrrell burner. And it has a little adjustment here, 2 adjustments. A lot of Bunsen burners aren't very adjustable, so this is a fancy version. This is a gas tube, rubber tubing here for gas. So we can move the burner. We can hold the burner in a hand, and that gives us a lot more control. Over here, there's another tap. This is labeled ICW, Industrial Cold Water. These industrial cold waters we don't really use. This is for providing a high-powered jet of water. A high-powered jet of water is another way to create a vacuum, but it's a huge waste of water. And then underneath here, we have our drawers here. When you come into lab here at El Camino, one of the drawers will be unlocked. The other drawers are for other sections. So you find the one that's unlocked. This is the lock here, or just a standard combination. And then let's take a look inside the drawer here. Oops. There's a tab here. You have to unlock the drawer by moving the tab up to the side. Then now we can unlock it here. Do you see the tab is connected to the lever that locks it? Excuse me. Are you okay with that beeping sound? Is everybody okay with the beeping sound? All right. Okay, when we go here, this is your check-in sheet here. And the check-in sheet, let me see, is it upside down or right side up? Right side up. Your drawer number is L19 here. L19, and it should be labeled L19 on the outside, yeah. You can see here, L19, it's labeled. I don't know if that's, I need to flip the camera, don't I? Let's see if I can. Yeah, let me just flip the camera. Let me see if it comes. Yeah, that looks right. Okay, excuse me. And so what you'll do is drawer number L19, this checkout you save for at the end of the semester. Here you'll just put in your name, last name, first name, and then you're responsible for all this equipment here on the list. And so we got to make sure that everything's present and that it's in good shape and reasonably clean. You'll also fill out this bottom section. If you have, sometimes we run out of drawers, so you have to share a drawer. And so if 2 students have to share a drawer, then both students end up signing this. We try to avoid that. We try to have enough equipment for each student. But in the rare instance that it does happen, you might have to share it. And both of you will be responsible. Now, both of you will be responsible for the equipment, and some of the equipment's cheap. Like test tubes are cheap. You know, test tubes are like 25 cents each or something. And so test tubes aren't that big of a deal, but some of the equipment is really expensive. And so let's go over here next to the exit door. You go next to the exit door, we can see, you know, how much the equipment costs. And so if you look, there's a burette. Burette is $183.50. This is 2018, 2019. Price has probably gone up. Burette's pretty expensive. Don't break burettes. Students break them though, and end up having to pay about $200. What else? Graduated cylinder is expensive too. You know, 90 bucks for a 500 milliliter graduated cylinder. In your drawer, you have a 10 milliliter, which is 27, and a 50 milliliter, which is 40. The others you check out, and hopefully you won't break them. We have environmentally safe thermometers. Those thermometers in the back are $31 each. Look at the platinum wire. You know, platinum's so expensive. A little tiny piece of platinum wire, $250. Don't lose it. Some of the other stuff we don't work with, distillation stuff, that's organic chemistry. This list is for both the organic lab and the inorganic labs. Oh, here's a fire alarm. That's our fire alarm there. You know what this thing is? This thing. You probably, if I go down here, you see that liquid in there? What does that look like? Yeah. This is a mercury barometer. And so this just measures barometric pressure. You can see this is our barometer. If there is a fire, like I said, this room is sealed. So if there's a fire, you're just supposed to leave. You're not supposed to play the hero and put it out. You're just supposed to leave the lab. Of course, if it's a small fire that's easy to smother, then go ahead and do that. You know, just use common sense. But anything big, get out and let it burn in the room. And so this room is kind of like a vault in a way. You know, the walls, the doors, the windows, everything's meant to seal in fires. And so you don't want to be sealed in the room with the fire, of course. And so the beakers are kind of pricey. You don't want to lose those, but not terrible. We have two sets. And so we have a 50, 100, 150, 250, 400, and 600. And they look like these cups here. Right there. And so let's take a look at the beakers here. The biggest one you have is 600. Now look at this one. This must be the 600. This must be the 400. The 400, two things. The 400 looks like it has hard water deposits in here, so it wasn't cleaned very well. And there are scratches. The scratches you can't do anything about. You know, eventually the glass is going to get scratched, but this should have been better cleaned by the last person. Last person probably was boiling tap water. And if you boil DI water, you aren't going to get those hard water deposits like that. There's a difference here. Now this beaker has graduations on it, and so you could record volumes on it if you'd like. So 250. 150, 100, and then a 50 there. Those are our beakers. So you look to see, is it clean? Well, this one's not so clean. The others are acceptable. And then you look for cracks. You know, you don't want to take responsibility if there's a crack. And sometimes there's a crack on the bottom you don't notice. And sometimes there's chips. If you look, I see chip, that the mouth of this is chipped right here. It's not too bad. Those are probably acceptable, but watch out for chips, because those lead to sharp edges. And if it's badly chipped, go get a replacement from the stock room. And so beakers are a common tool. So we have two sets of them here. Oh, this set is clean. Yeah. This is what the 400 should look like. Okay, now they labeled it. It says HCl acid on here, but that's easy to clean off. Just get a piece of paper towel. You can clean off that labeling on there. This is a lot cleaner, but still it's not that clean. Could be cleaner. This one has got some hard water deposits there on the bottom. All the white haze. Sometimes it scratches. If it scratches, there's nothing you can do about it. But we got 2 sets, so you want to inspect those, you know, make sure they're okay. And so that checks out. We got 2 sets of beakers, 12 beakers altogether. 12 beakers. This is Pyrex glass. Pyrex glass is pretty good. It's pretty tough. But still, you can break it and drop it. Then we need crucible tongs. These are the crucible tongs here. You know, you can handle hot crucibles with these. And so this is a crucible tong. What's a crucible? And so do we have any crucibles in here? Well, we don't have any crucibles in here. Crucibles are little ceramic bowls that you can grip with the tongs and set them on the ceramic plate there, you know, hot crucibles. 1 crucible tong, and then Erlenmeyer flask. Erlenmeyer flasks are cone flasks, 25, 50, and 125, 2 each. So we should have 2 sets. The 25s are these guys here, small 25 milliliter Erlenmeyer flask. Nice thing about Erlenmeyer flask compared to a grad cylinder is splashes. When you have splashes, you know, things can splash out of beakers quite easily. But it's a lot harder to get splashes out of an Erlenmeyer. So Erlenmeyer does a better job of containing the liquid in the container compared to a beaker. But they're harder to clean too. So there's trade-offs, of course. Here are your 50s. So these look okay. And then your, how many? 125s. We should have 2 125s. So 2 125s. And then 3 250s. So 3 250s. The 250s are the bigger ones. So 1, 2, 3. Now, they don't look all the same. You see that? Like this one's a lot thicker here when you compare it to this one. This one's a lot thinner. In fact, this one weighs a lot more than this one. This one's really light. They aren't all the same. So don't worry about that. They all should work. Although this one would be a nicer one to have. This one's just a lot more glass, a lot more quality, a lot more difficult to break. But you have no choice. You're just given with whatever you're given. Okay, now we have Florence flasks. Florence flasks are round with a flat bottom. And so this would be a Florence flask here. It's round and it has a flat bottom. Usually a long neck Florence flask. These are good for storing liquids. You know, we use Florence flasks for storing liquids. That's a big one. This is a small one here. Let's see, you can see the label on this one, maybe. It just says, the label just says Pyrex, 250 milliliter, made in the USA. So, this is Kimax, Kimball, you know, this is a brand. Kimax is pretty thick. This is a lot thinner. Pyrex, you can tell if you have Pyrex because if you look endwise, do you see the green color? You know, when you look through the long part of the glass, it appears to be green. There's a slight green color to it. That's because Pyrex contains some iron, and that iron causes it to have this green color. So we got that. Then we need a short stem funnel, one. This doesn't look like such a short stem funnel, but this is what we call the short stem. There's even shorter stem funnels. This is the stem part. You got a funnel here. You can do some filtering with the funnel. And then glass rod with a rubber policeman. And so we use this as kind of just like a kitchen tool, you know, spatula. If you have a spatula at home, you know, this is like a miniature spatula with the glass. Now the glass comes in handy because you can mix liquids with glass. Like, so if we flip this over, then we can use this as what's called a stir rod and stir things with that. Glass is you know, less susceptible to contaminating your chemicals. And so that's a glass rod with a rubber policeman. Graduated cylinders, 10 and 50 milliliters. These are expensive. This one's $40. People leave these out all the time. And they disappear. It's $40. This is $30, this little one. This is a 10 milliliter grad cylinder. Matches, we have matches here to light the Bunsen burner. Now the matches these are free, basically. If you run out of matches, you can get these from the stock room. So we never worry about the matches. There's plenty of matches. Medicine dropper. So we have a little dropper here. This is glass with a little rubber bulb. We also have disposable polyethylene ones. They're all plastic. So this is a glass medicine dropper with a rubber bulb. A spatula, well, we have the rubber spatula, you know, the rubber policeman over here. We also have a stainless steel spatula. And so this one, stainless steel, but it's quite stained from being corroded and getting hot. And so this comes in handy as well. Test tube clamp. Test tube clamp is this, and you just squeeze it, and then you can grab test tubes. So you can grab a grad cylinder too. Yeah. So. Test tube clamp, test tube rack. This is our test tube rack. It's this plastic holder. We got a bunch of test tubes in here, 2, 4, 6, 8, 10, 12. 12 test tubes in there. Test tube rack 1 and 2 large test tubes. They're here. These large test tubes can fit in the rack here. You know, this rack is broken, but it has at least one tab left. The other tabs are broken. But if you put these in here, you can't shut the drawer, unfortunately. So we'll leave them out. So we got these large test tubes here. And then we got these small test tubes here. This is painter's tape. And so people label their test tubes one of 2 ways. They either put some painter's tape there and just write with a pen, or they use a Sharpie and just write directly on the glass. And so this HCl that was labeled here is just Sharpie. It's a blue Sharpie, and you can do that. Also, this white panel here, you can write with pencil on the white panel. You want to label with beakers. There. All these have a white panel for labeling with a pencil, if you like. That's what the white panel is for, labeling. This one, not so easy, probably. If you use a Sharpie, of course, anything's easy to label on. All right, we need small test tubes, 12. And here, the same thing. We want to make sure they're not broken. A lot of people don't even look. You know, they could be heavily damaged in the lips. We should check them all, make sure. Also, test tubes tend to crack and fracture at the bottom. You know, the reason they crack and fracture at the bottom is people are using their stir rods like this. Here, let me show you. This is, I'm using a webcam here. Handheld. And so if you're doing this all the time, stirring it with the stir rod all the time, eventually you could crack the bottom of this. You know, you're causing a lot of mechanical strain on the bottom of the test tube, and it can easily break or crack. And so you check for fractures, little star, call them star fractures on the bottom test tube. These test tubes look pretty clean. And so, you know, if I got these test tubes, I'd be pretty happy with them because they're all fairly clean. Just because it looks clean, I still clean it before using it because I don't trust, you know, and you shouldn't trust the last person. The last person probably wanted to get out of here ASAP, so they probably didn't clean it as thoroughly as they probably should have cleaned it. And so we got the 12, and then we got 2 watch glasses at 100 millimeters. Okay. These are our watch glasses here. Oh, we got 3. And so that happens too. Oops. Pyrex is pretty rugged. That was $30 graduate cylinder right there, and it didn't break. But if you drop it on the floor, it's going to break. And so they gave us 3. It's marked as 2. So sometimes we're short, sometimes we have extra. So we could leave one of these out or just leave it in the drawer. And those are watch glasses. Watch glasses act as covers for beakers. So we can cover the beakers like this, you know, or we can cover it like this. Watch glasses are also small places where we can look at crystals and do other things. Watch glass, lots of uses for watch glasses. Sometimes we have to cover, like in Chem 1A, we have to cover Erlenmeyer flasks with a watch glass. Well, that's very dangerous. So a lot of these get broken because what happens is people carry this to the balance and it accidentally falls off and then drops to the floor. When it drops to the floor, it's going to break. The drawer is lined with paper here. It's pretty dirty. Unfortunately, we don't have new paper. And so that's the equipment. Once you're satisfied, everything looks good, then you fill this out and you turn this in. But before you turn this in, you have to write down the locker combination. You know, in this case, it's 31-1-15. And so does everybody know how to use these combo locks? I'll just assume everybody does. If not, then certainly. So you check it first, you know, make sure it opens, you know, otherwise maybe they made a mistake, maybe the wrong one. So 31, 1, 15, and that's it. So that looks good. Another thing that people do is they forget to lock up their locker when they leave. And then the next time they come in, they say, oh, you know, a whole bunch of my equipment is missing. You know, well, that happens. And this happened before in the past, unfortunately, where they ended up losing a lot of their equipment. But what can you do? Okay, so that's the check-in procedure. And then when we're in lab, we get the layout of the lab. Like, if there is a fire, how can you get out of this room? You know, which exits do you use? Well, we only have 2 exits there. Each lab has 2 exits. If there are 3 doors in the lab, then one of those doors leads to a closet, and you can't get out that way. Unfortunately, we can't get, if there's a fire, we can't get out these windows. Those windows are sealed shut. They don't open. Even though it looks like they open, they don't open. They're sealed. And so you can't get out the window. You got to get out that way, and hopefully the fire isn't that way. You know? You want to know where the eye wash fountains are, because if you get something in your eyes, you can't see. And you have to be able to find these with your eyes closed. I mean, or get help, you know, you ask for help from other students. Other students will be able to guide you to the eye wash fountain if you get something in your eyes and it's burning terribly bad. You can get over to the eye wash fountain. You know, the sooner you get there, the less damage there's going to be. But hopefully there's no damage because you'll be wearing your safety goggles. Today's lab, we don't need safety goggles. I'll talk more about safety rules as we go along. And so let's move on to today's lab here. And so this is the equipment here. And what I'll do is I'm going to move stations here. Well, I'm back to the front here where it's beeping a little louder, but I need my book here and I need some room here. So the version I have of the lab is the older version here, the 2000, but I don't think much has changed between the old version and the new version. So since the school won't give me the new version without buying it, unfortunately. If you ever forget what the equipment looks like, it's all here, you know, common laboratory equipment. Here. Plus additional stuff, evaporating dish, which we don't have, screw clamp, pinch clamp, burette clamp, crucible, etc. This is what the burettes look like. Those are $200 a piece. Expensive. We're going to use that semester. Erlenmeyer, Florence. These are volumetric. We're going to use those, etc. Mortar and pestle we don't use. Glass plates we do. These are the safety rules here. So you should read through the safety rules. Most labs, they give a safety quiz. Like when I was at UCLA, we had safety quiz. Yeah. So we had to read through these and make sure. But you read through these here, and then you sign what's called the safety contract. And so this will be a quiz. Actually, did we do a quiz today? We haven't done a quiz today, did we? And so the quiz today is going to be this. Read through the safety rules. And if you have any questions on the safety rules, you can ask me. But eventually, you're going to have to turn in, once everything makes sense to you, fill this out and then upload it to Canvas. I'll have a place where you can upload this. So I have read the 7 listed rules for laboratory safety. 7? Oh yeah, I guess there's 7 with multiple parts. Okay, and then fill it out, put your student ID number, signature, and date it, and upload it to Canvas. All right, this is the experiment we're doing today. Actually, we're doing 2 experiments today. The first experiment we're going to do is the laboratory burner. This one doesn't take much time, so that's why I want to do a little catch up today. And so, okay, student ID and what else? Let's take a look. Just signature. Yeah. You should have a copy of this, I think. But I'll do this here. You could read through this. That's page 1. If you don't have the lab manual yet, it's okay. Let's take a look at page 2. This is 2 pages. It's page 2. And this is that. Are you going to upload this page so we can write on it? Yeah. All right. That's easier. I'll do that. Do you have, everybody should have a copy of this though, because you're going to have the report sheet to write it, or I suppose you can just write it on a regular blank piece of paper, but there's stuff in here that we're going to need nonetheless. So you may be able to get by. I know some of you don't have it. I forgot who was out of the country. But anyway, here, this is our first experiment. So normally what you do before coming into lab is you have to read through the experiment, you know? And so, and then we have a lab notebook. And so in Chem 4, lab notebook is not mandatory, but usually I make a lab notebook mandatory in Chem 4. And I'll show you what a lab notebook looks like. Maybe I have an example of some students. Let me see. Hold on just a second. I have some examples of a lab notebook over here. They really cleaned out the lab, so there's no lab notebook there. So the lab notebook is, so the purpose, one of the purposes of the lab notebook is you want a set of data for yourself. And so this is the report sheet. And so what a lot of people do is they write all their data onto the report sheet. And then they turn this report sheet in. Now, let's say you write all your data on the report sheet and you turn it in and somehow I lose it. If I lose it and you gave it to me and you gave me your only existing original copy, then it's lost forever. And so you need a permanent copy for yourself. So this is why, you know, rather than writing it all in the report sheet, which you turn in, you write it into your lab notebook so you have a record of it, and then you transfer the stuff into your notebook. And this does two things. One, turning in a nice and neat report sheet is better than turning in a dirty, messy report sheet. You know, a lot of people who grade reports, neatness counts. You know, for some people they don't care, but a lot of people do care. And so in scientific reports, usually they're pretty nice and neat, not with a lot of corrections and a lot of errors and a lot of scribbling around on it. And so this is why you do all the errors and the scribbling around in your lab notebook, so that you can turn in a pristine report to leave a very good impression. And so this just, and then there are other reasons for it, which we'll talk about later. All right, so the objectives today are to become familiar with the laboratory burner and its efficient use, to gain experience using the burner in the manipulation of glass tubing and glass rods. We might skip that, or I might do it. To be introduced, I'll probably do it. To be introduced to a chemical reaction, to observe and optimize the combustion reaction produced by various burner settings. So we'd read the discussion. Many experiments require the application of heat. If an open flame is not to be hazardous, gas burners need to control the heat production. The common source of this heat is the heat energy released when a fuel such as natural gas is burned in air. Natural gas is mostly methane, a little bit of ethane, and some mercaptans. Mercaptans are the thiols that stink. Almost all laboratory burners used today are modifications of the original Bunsen burner invented by the German chemist Robert Bunsen. A lot of chemistry history is centered in Germany. A lot of chemists actually chemical discoveries happened there. One of the more commonly used modifications called the Tyrrell burner. Bunsen's fundamental design is also widely used in domestic and industrial gas burners to operate the, et cetera, et cetera. So anyway, the burner relies on methane. So methane and oxygen gas yields carbon dioxide, water, and energy, heat and light here. So this is the reaction in words. Let's see the other reaction in formulas. No, they don't, but I've written it many times. All right, so the burner that we're using is called a Tyrrell burner, which is a fancy Bunsen burner. And there are parts to the Tyrrell burner. So let's take a look at the parts here. We'll just look at the real one here. All right, when I look at the parts, let's see, probably want to point it. Down. Okay. On the top here, this is the barrel. And the barrel you can screw out. You can screw this off completely. So let me screw up the barrel. Just counterclockwise. Loosens, clockwise tightens. The barrel's just a tube. You know, got this little screen at the top here. It has these holes, these ventilation holes here on the side. There. Yeah. If you look here, you'll see a little orifice. Let's see, I'm not sure if I'm pointing at that there. That little orifice is where the gas comes out. And the gas that's coming out is pretty much just natural gas, no air. There's no air coming out of this tap here. So if I open this here, that's just natural gas coming out. In fact, let's see what happens if I light that. I'm gonna light that there. So when I light the natural gas, I'm going to turn on the gas first so I don't fill up the room. Or actually, I'm not going to turn on the gas. I'm going to light the match first. So light the match, and then let's see what happens without the... I don't get a very good flame there. And it's not stable. It's just being blown out. It's being blown out because there's no air being mixed in there. It's just gas. And so what I have to do is I have to mix the air with the gas here. And that's the purpose of the holes in the barrel here. I can adjust the amount. I can also adjust the amount of gas coming out because on the other side of the orifice is a little needle. And that little needle I can unscrew out by turning this. By turning this counterclockwise, I can unscrew the needle out. In fact, I'm going to completely unscrew the needle out. Now, the needle is just for fine control, but you know, some people try to use the needle to shut off the gas. We don't use the needle to shut off the gas. And that's why you can see that the needle should be a nice cone, but do you see this cone is dented? Some paper towel here, there's grease on here. I don't know if you can see it very well. Wipe off some of the grease. Oh, this one's not bad. Some of these are heavily dented. You know, it's supposed to form a nice cone at the top, but what happens is people use this to try to shut it off and end up over tightening it. When they over tightening it, it jams into the seat. The seat is the other side of the orifice that's inside here. And it ends up putting a big dent in there. And when you put a big dent in there, it's hard to adjust the flow. We want a continuous adjustment. It turns into quantized adjustment where there's a huge dent in there and you open it a little bit and it's wide open. And so it loses its fine control. The shutoff is always here. This is our gas shutoff valve here. When the valve handle is perpendicular to the line, it's shut off. When it's parallel to the line, it's open. You can hear the gas coming out of there. And so here, open, closed here. Now, you don't have a nice quarter turn. Unfortunately, you have those. I don't know why they didn't put quarter turn ones on. You have little handles that you got to keep twisting and twisting like this. Now I really smell the gas. So fortunately, the gas is odorized with stinky thiols, but not terribly stinky. I can survive these thiols without too much damage. So this needle valve looks okay. And so I'm going to put the needle valve back in to the base here. And so this is going to serve as fine. But you could potentially shut off the gas, you know, but I want to really. This is just meant for fine control. So I'll just turn it clockwise. So get it all the way in there. Okay, you never bring it to a hard, tight stop, you know, just a gentle stop here. And then it's sealed off this whole little hole here. So let's see. So I turn on the gas, you can barely hear anything. Then I open this. Okay, I can hear more and more gas coming out. You probably have a hard time, it's noisy in here. But this one allows you to control the amount of gas. It smells in here, so I'm gonna shut this off. Okay, and then I'm gonna replace the barrel on here. It looks like somebody cleaned these, so that's good. You know, somebody cleans them. The problem is they get dirty. Stuff gets in there, and you get a really bad flame. And so when we want to light the burner itself, we've got to make sure it's open here. So I'll unscrew that out. We've got to make sure there's some air in here, or we could close it off so there's no air. If I screw this all the way down, it kind of blocks off the holes of the barrel. I'm going to just screw it all the way down for right now. And then when I light this, you know, I got to make sure I don't smell any gas. So the gas has got to be dispersed. And then I'll light this. So I'll hold the match up here. I don't know if you guys can see that. Okay, I'll hold the match up here, and then I'm going to turn on the gas slowly at the main valve, and then light it. Okay, I'm going to shut off the lights. You can see it. This is not a good flame. You see the yellow there? The yellow is telling me there's a lot of soot being generated. You know, it looks pretty blue down here. That's good. But up here, you see a lot of yellow. The yellow are glowing soot particles. You know, and that's what's causing the yellow. There are other reasons we might get a yellow flame, like if there's salt around. But this is not. This is a clean burner, and so we're not getting good combustion here. In fact, there's not enough air going in, and that's creating soot. And if there's soot, there's carbon monoxide. So right now I'm probably inhaling carbon monoxide. And so I shouldn't leave a flame like this in this condition because it's going to generate some carbon monoxide. But in a lab like this, it's totally different than a house. In a house, I think you get about maybe 1 room change of air. You know, the ventilation isn't so good in a house, but in a lab like this, the air inside this lab is exchanged maybe about 5 times an hour. So all the air in here is completely changed to fresh air 5 times an hour. So I'm not too worried about the carbon monoxide right now, but I want to get rid of the carbon monoxide. So the way to get rid of the carbon monoxide is to make sure there's enough oxygen. Make sure there's enough oxygen. I'm going to unscrew the barrel out here to get more air. Now look at the flame here. Do you see how much less yellow there is in the flame? So yellow flame is not good. The blue flame is good. And so I can do more. So I'll get more and more. If you get too much air, take a look. It could blow out the flame. You see there's a lot of air there. And you get a more unstable flame because too much air could blow it out. Like, for example, if I blew it out right now, I probably could blow this flame out easily. Just with a little breath, you know, blow it out. Now, I got a lot of gas coming out of there. So either I got to shut it off or I got to do this quickly. But anyway, that's too much air. So let me back that out here. And so I'm going to screw this in so there's less air. Okay. I'm looking at the base. Okay, now that looks more stable. That looks like a stable flame there. But this flame doesn't have much structure. It looks fairly homogeneous. That's not the hottest flame. The hottest flame is if we get some structure in there. And the structure is, what I want to do is I want to turn down, I have too much gas. I got too big of a flame. for this burner. This burner is not meant to have that big of a flame. And so I'm screwing this in using the needle valve here. And so I'm screwing it in with my fingers. I know it's hard to see because there's not much light. Okay, now look at, do you see the flame now? When you look at the flame now, that's a good structured flame. There's a nice cone on the inside, and then there's what we call the outer cone on the outside. When you see a flame like that, that's a nice hot flame. We can make this a little bit bigger. I'm going to turn up the gas a little bit and adjust the air to make it a little bit bigger. And then increase the gas a little bit and then increase the air a little bit, make it a little bit bigger. Okay, so now that's the kind of flame we want, you know, a flame that has a structure to it, you know, with a nice cone there. Now, the different parts of the flame are going to be at different temperatures. The hottest part of the flame is going to be right at the tip of the cone. So if I take a matchstick, this is just a matchstick here. If I take a matchstick, I'll put it in different parts. Like if I put it right at the base, you see the matchstick doesn't light up. Because if I put it right at the base of the flame, here, it doesn't really catch on fire, just to the edges maybe. It doesn't really catch on fire. And so it's mostly unburned gas right at the base. And inside the cone is unburned gas. But if I put the matchstick right at the tip of the cone, do you see how quickly it ignites? It ignites quickly because it's so hot there. That's the hottest part of the flame right there. Let's try that. I'm going to put an unburnt match head in there. I could put the unburned match head right in the center there at the base and nothing's going to happen to it, you know, right there. Oops, eventually got hot enough, but really nothing much was happening. But if I put that match head right at the tip of the cone, forget it, it's going to light immediately. It's so hot there. So the coldest part of the flame is right at the bottom. The hottest part of the flame is right at the tip of that inside cone. We call that the inner cone, the light blue cone. Now there's an outer cone there too. The outer cone is this part here. That's the outer cone. The outer cone's like medium heat. And so up here, it's like more medium heat. Oops, I blew it out. I'm gonna shut it off a second. So, shut it off so you shut it off because you don't want to fill the room with gas and then have an explosion when you light it, try to light it. Now what do you do with all these used matches? Used matches, let them cool down, you know, but don't, you can let them cool down on the ceramic plate if you want, if it's hot, this is a ceramic plate. Then you can throw them in the garbage. Not every burner is going to be so kind to you. You know, some of these burners are kind of old and the needle is getting all screwed up and they're dirty and the inside, the orifice is clogged. A lot of little problems can prevent you from getting a decent flame. Okay, but that's it. All right. All right, so I talked about lighting the burner. You don't have, you know, you don't have to be as strict as they are lighting it as far as procedure goes. Characterizing luminous flame. Luminous flame is a flame that glows yellow. We don't like luminous flames. Because all the air is closed off. If all the air is closed off, we get yellow flame. The yellow is from glowing soot particles, which are carbon deposits. There's not enough air, and we're getting carbon monoxide. Luminous flames make carbon monoxide too. So we need more air. So we unscrew the barrel, let more air, and then we get a non-luminous flame. This is the non-luminous flame. Can you see it? It's pretty hard to see. It's hard to see. Let's put it against black background. Hard to see. And so, but we have an inner cone and an outer cone. Characterization of combustion products. Hold a large, dry, cool beaker inverted 15 centimeters above the top of the non-luminous flame. We don't have to measure this. We just guesstimate 15 centimeters. Note the condensation inside the beaker. All right. So I'm gonna grab a big beaker. So I'm gonna use a 600 here. I'm gonna invert it, and then I'm gonna hold it above the flame like this. And take a look, do you see how foggy the beaker's getting? You know what that is? When methane combusts with oxygen, what forms? So let's do that here. Well, we have methane gas plus O2 gas yields what? Yeah, H2O. We get CO2 and water. CO2 gas. Now the water initially is going to be in the form of steam. Steam. Eventually it's going to cool down to liquid. It's not going to stay steam forever. So it's gas, and then it'll cool down to liquid. L. Okay. Balances will need 2 O2s and 2 water. And so what we're doing is we're catching the steam and condensing it on the inside of this beaker. Once the beaker gets hot enough, then it's hard to condense it. So it has to be a cool beaker. So let me get another cool beaker here. Let's capture some more steam. So if I look at this beaker here, I don't see any fog or condensation on it. And I'm gonna hold it above the flame, and then you can see it fogs up quite rapidly. There. You could do the same thing by exhaling in it. And so, well, it's not going to stay steam forever here too. You know, it's coming off as steam, but eventually it's going to cool back down to liquid water. Ooh, it's getting hot. It's a nice hot flame. All right, is it break time? Yeah, I guess it's, all right, let's take a break then. Okay, we're going to take a break for 15 minutes or so. 15 minutes, so 35, 40, 50. We'll come back at 3:50, okay? So I'm going to pause the recording here. Yeah, that's correct. We need to light the match first. Otherwise, you know, if we turn on the gas and we have trouble igniting the match, we're going to fill up the room with gas, and we could have an explosion. Yeah, and so to prevent the risk of explosion, you know, or filling up the room with gas. Yeah. Well, the quiz, actually today's quiz, this is what we're going to do. This is part of the lab. And so the quiz is just a standard quiz, 4 points. But you're going to fill this out, and then you're going to turn this in. And this is worth a lot more points. How many points is it worth? 20 points? I forgot what I assigned it. you know, either 10 or 20 points, 10, 15, or 20 points. And so this is going to be your lab. And so it's not a quiz, it's a lab. But we're just going to go through. I'm just going to show you. 2, why must the methane be mixed with air in the barrel before it is burned? Because if we don't mix it in the barrel before it's burned, do you remember what color it was? You know, when I closed off the air holes here, what color was the flame up here? Yellow, right. And so what we have to do, there wasn't enough air. Even though this room is filled with air, we still got a yellow flame. How could that be? Well, it's because we need to mix it, pre-mix it, you know, before. And so we just can't have the methane and the air come in contact here. We just don't get the right mixture. So what we have to do is we've got to get the right mixture of air to methane down here first, and then we'll get it. And so we have to do it to get the right mixture to prevent a yellow flame. 3, what is the color of the flame when the air inlets or holes are closed? Well, this is just the same thing. You know, if we don't mix the air first, it's going to come out yellow. We don't want yellow, we want blue. And so we got to pre-mix it. What is observed when a crucible is held in a luminous flame? Why does a luminous flame do this? Did I skip that? Yeah, I did. Unfortunately, I skipped that. Hold a crucible in luminous flame for several seconds using crucible tongs. Note the color and character of the deposits on the crucible. So let's go ahead and do that since I forgot to do that here. So I'm going to get a luminous flame. So what I'm going to do is I'm going to close off the air holes by just screwing the barrel in all the way so the air holes are covered. And then I ran out of matches, but that's not a problem. I just go to the stock room and get a new box of matches. The stock room is where you'll go quite often to check out specialized equipment. It's out the door across the hallway. There's a window in the hallway that's called the stockroom window, and there you can get supplies. And so I'll walk over there, get a new box of matches. And so I'm supposed to light the match first and then turn on the gas. So let's do that. And turn on the gas from the main valve over here with my left hand. And then I should get a luminous flame. But this isn't too bad. I mean, this is still fairly blue. It doesn't have the structure. Let me turn off the lights. However, what I'm going to do is I have the gas turned on max at the main valve. So what I'm going to do is I'm going to open up this by unscrewing this out, you know, counterclockwise. And so I'm going to get a big flame like this. And now when I look at the big flame, it's quite yellow, you know, especially at the end there. Okay, now I'm going to get a crucible. This is a crucible, and it's just a porcelain dish. You can do high temperature reactions here. And so if you want to cook something in the flame, you can use the crucible to do that here. And then you have a pair of crucible tongs in your drawer. You have crucible tongs, but no crucible. Well, fortunately, I got a crucible. Normally, we hold crucible tongs like this, you know. But in this case, I'm going to grab it on the edge like this because I'm going to coat the surface with whatever soot. So the purpose here is I'm going to try to coat it. Look how clean the crucible is right now. It's pretty white, and it's pretty clean. And then I'm going to hold it up here in the yellow part of the flame to see if I can get some soot deposits on my crucible. What is soot? Soot is just carbon, you know. So I'm seeing if I can get just carbon deposits here. Take a look. This burner is burning still pretty clean. Even there's much worse burners. So I'm not generating a huge amount of soot. This is going to take longer than a few seconds, probably because my burner is burning pretty efficiently. Cordless. All right, maybe let's check it now. And so what I'm going to do is I'm going to cool the crucible. I don't want to touch the crucible with my fingers because that's one of the most common accidents in lab, or burns. And so I'm getting the ceramic plate with the matches on there. You dump the matches in the garbage. And I'm going to set the crucible on top of the ceramic plate and let it cool that way. Let's turn on the light. This is not a very sooty flame, unfortunately. It's not very sooty flame. Take a look at the crucible. I'm still not going to handle the crucible with my fingers because it's still very hot. These other black things are spills, but you can kind of see there's a kind of a light black coating of soot on there. It's hard to see, but maybe if I flip it this way, on this side there shouldn't be much of a light black coating between the spots. This isn't the cleanest crucible, by the way. And then over here, I can see it's grayed a little bit. It's not as bright and white. And there's just a very, very thin coating of soot on there. Let me see if I have something that's much more sooty. So if I got a really bad burner, this is what it looks like. This is called an evaporating dish. Evaporating dishes are used to evaporate liquids. This is what a clean one looks like. This is one that's captured a lot of soot. So somebody must have held this one upside down in the flame for a while. And you can see the difference between clean and sooty there. And so this should capture more. So if I held this one like this, and again, you know, I'm not seeing much yellow here in this flame. This flame is not a very sooty flame. It's just the burner is pretty decent. Even poorly adjusted, it's pretty decent. Can't say the same for a lot of the other burners here. Let's see if we generated much soot in this one. Oh yeah. You can see it's a lot sootier than it was before. This is very hot. I'm not going to touch it with my fingers, but I'll touch the cold one. You can see it's getting a lot sootier. All right, that's enough of that. There, and I don't want the yellow flame. Yellow flame, remember, soot and carbon monoxide. So I can open up the barrel by unscrewing it out here. Get a decent flame. This flame's too big to get a cone. You know, it's too big to get a cone. You can barely see the flame because the lights are off. And so I'm going to screw in the needle valve clockwise to try to get a cone. In other words, try to make a smaller flame so I can get a decent cone there. Yeah, you can see it, barely. There's a cone there. I'm going to shut it off. Okay, so going back to the quiz here. Oh, I didn't do, these are the questions, I guess. What is observed when a crucible is held in a luminous flame? Why does a luminous flame cause this? Well, it's caused by incomplete combustion. Well, what's observed is soot deposits, and what causes it is lack of oxygen. And so here we have a stoichiometric amount of oxygen. And if we take methane and not add enough oxygen, that is too little oxygen, what we're going to get is soot, carbon monoxide. Soot is solid. Carbon monoxide is a gas, and maybe some carbon dioxide. You might get a mixture of these things. It depends on the conditions. This is more skeleton to try to figure it out, and water. And so this isn't balanced because I don't know how much soot and how much carbon monoxide and how much CO2 is formed in that. So that's the reason I didn't particularly balance that. Let's see if you can see that now. All right. Okay, did everybody get it, basically? All right, so what is observed? Soot deposits. Why does luminous flame cause it? Not enough O2. Too little O2. What is required to convert a cooler luminous flame? Luminous flames aren't that hot. To a hotter non-luminous flame. So if I want to get rid of the yellow, what do I need more of? More O2, yeah. More oxygen, more air. That's what I need. Draw a diagram of a non-luminous three-zone flame. So this is the match or the splint test. So let me put that here. So here's the top of the burner here, and then the flame is like this, you know. It's a little more pointy than this. This is the outer cone here. And then inside we have the inner cone. Oh, this pen is dead. Inside is the inner cone. And then the temperature regions, here it's going to be the coldest. At the bottom, it's the coldest. At the top of this cone here is going to be the hottest. And then up here is going to be medium. At the top of the main, or the outer cone, medium. Heat. So, actually, I need to blow this up. See if I can blow this. It's hard to see this. Okay, I can see it a little bit better, but still hard to see. 3-zone, 4-zone, whatever you want to call it. All right, so that's the, we use the match. I showed you with the match splint earlier. You know, that's how we determined what was hottest, is how quickly it ignited. What is the condensate that forms inside the beaker when it is held above the flame? Well, you guys already answered that. What was it again? It's H2O. H2O liquid. Water. Good. Where does it come from? Well, it comes from a product of combustion. It comes from combustion. And so take a look at the combustion reaction. Methane plus O2 gives CO2 and water. The condensation is the converting the gas, yes, steam into liquid water. Why should cut glass or chipped glassware always be fire polished before using? I didn't talk about fire polish. This is glassworking. Unfortunately, glassworking glassworking is a good skill to have. A lot of professors here didn't like it, and so they voted to get rid of it. I liked it, but that's just me. But still, let's talk about fire polishing. What happens is sometimes you get little chips, and little chips mean that, you know, you don't necessarily have to throw it away, you know, your equipment. What you could do is you could do something called fire polishing. And so let me show you what I mean by that here. See if I can get something that's good to polish. We have, okay. Well, somebody went through and got rid of all the stir rods. We had a whole bunch of little tiny stir rods. These thick rods are very hard to fire polish with our Tyrrell burners. The Tyrrell burners just aren't hot enough to get it. But you see how sharp that chipped edge there could be? You know, it's fractured there. And so what we can do is we can melt some of that sharp edge off there. And the way we melt it is by a process called fire polishing. And so if we have some sharp edges that we want to soften, that is round, ooh, then what I'm going to do is I'm going to get a bigger flame here and then try to get a nice cone. Let's try to get a nice cone with this. If you have too much gas, it's hard to get a good cone. So sometimes, you know, you think a bigger flame is always better, but sometimes a bigger flame is not always better. You know, so I could have a huge flame, but there's no cone, there's no structure there. And that's not very hot. What I need to do is I need to concentrate or focus that heat into a tiny point. And so even though it seems like counterintuitive, a smaller flame can be a heck of a lot hotter. So this little flame here is a heck of a lot hotter than that big flame. So I turned it down so I get a nice cone there. And then what you do is you put the tip of the stir rod there and then just rotate it right at the tip of the cone. And the purpose of this is just to melt the glass to soften the edges here. Now this yellow is totally different. Do you see the yellow flame there? That yellow flame is totally different. This yellow flame is not because of soot. This yellow flame is because of sodium. There are sodium ions inside the glass. And when sodium ion is burnt in a flame, it gives a nice yellow color like this. This looks like sodium street lamps. If you have sodium street lamps have sodium vapor in there, and they made a light out of sodium atoms, and it gives off a yellow color like this. The advantage of sodium street lamps is it barely uses any electricity, and you get light. The disadvantage is it looks yellow like this. It's nowhere near white. But we keep heating this, so this glass has a lot of sodium in it. Sodium's everywhere, so oftentimes we'll see a yellow flame. I told you there are two reasons we get a yellow flame. One is soot, the other is this, sodium. And so we'll just keep heating it until it starts to melt on the end. You can see it'll glow. You can see it's glowing. Do you see it's glowing? It's melting. It's very hot. This is emitting red light right now. Don't touch it. Right now it's emitting infrared. You know, you don't see it's glowing, but I feel it radiating infrared radiation. Infrared radiation is invisible. I'm not going to touch that glass because if I touch that glass, I'm going to get burn, for sure. But what it's going to do is it's going to melt the sharp edges down. This is very hot, you know, even though it doesn't look hot. This is why burns are so common. The glass, you can't tell the difference between hot glass and cold glass. It looks the same. You can feel it. You can feel it radiating heat. That's one way. But you can't tell the difference by visually looking at it. So a lot of people just grab it by accident and end up burning. And maybe this is one of the reasons why they stopped doing fire polishing. I had a student, you know, whenever you have hot glass, you always point the hot end away from you, and you never give the hot end to somebody to grab. Like say, hey, check out my fire polishing. They grab it, second, third degree burn. It happened to me once. The student wanted me to check out their fire polishing and gave me the hot end. It was still extremely hot. I ended up getting second degree burn on my finger. Accidents happen. I couldn't tell. Okay, now look at the end. I don't know if you can tell, but it's a lot more rounded. You know, it's kind of melted. This is not focus. This is focal point. Is out there. But it's a lot more rounded. Softened. So that's fire polishing. So you can see here they're doing fire polishing, rotating it at the tip of the inner cone. We have wing tops here. This is for bending glass. For bending glass, you want to heat up a large area so you don't get too much of a kink when we bend glass. We bend glass all the time, so I could put a bend in this, but I'd want a wing top here. Otherwise, I'll get a very sharp kink here. If I melt the center here and then bend it, I'll get a very sharp kink. Sometimes people put a hook, you know, they'll put a grab handle on the end. So what they'll do is they'll heat it here and then bend it so it's easier to grab, you know, rather than just a straight rod. They'll bend it around to make a little hook. Okay, that's fire polishing. Let's go on to the next one of those 414. All right, then we have a true-false quiz. So I'm going to leave the true-false quiz up to you guys to finish here. This is going to be part of your lab report. And then what you're going to do is you're going to complete this and then submit it for, this is going to be experiment 1, report 1. And so this is a full credit lab here. The true-false, natural gas is primarily the chemical methane. If it's false, we have to change it. Let me give you an example where it's false. The purpose of the burner is to mix fuel with the nitrogen and air. That's false. The purpose of the burner is to mix fuel with the oxygen and air. So if it's false, we'll check off false, but we'll have to cross this out and then write the correct answer. The correct answer would be oxygen. True, false. The hottest part of the flame is the center just above the barrel. That's false. That was the coldest part of the flame. And so what we should say is the hottest part of the flame is in the center just above the inner cone. And so we change the underlined word to make it true. True, false. A yellow flame indicates an excess of air. That's false. A yellow flame indicates a lack of air. So we change that. So we'd mark false here. 5, a bluish flame with 3 distinct zones is the correct flame to use in most laboratory work. That's true, so we'll leave it. 6, to increase the amount of air mixing with the natural gas, screw the barrel of the burner upward. That's true. If the burner operates with a roaring sound, increase the amount of air. No, usually roaring sound means you got too much air and it's going to blow out. Let's hear that again. I don't have enough gas to make it roar. or too much gas. Usually the roaring sounds too much gas. Or too much air. Let me see, what was the question again? Increase the amount of air. No, we don't want to increase the amount of air. If this roaring is too much gas, whether it's air or methane, we've got to decrease the amount, so it's false. All right, so that's how you're going to answer these. So do 8, well, actually do all 9, 10, 11, 12, 13, 14, 15. You could put just the answers if you don't have this, just put the answers in. Here are the questions. Okay, everybody got it? Well, this is going to be on the recording, so you'll have it on the recording. That's the end of experiment 1. Okay, now what we're going to do is we're going to go on to experiment 2. So let's do experiment 2. Sure, I got all my pages here. Experiment 2 deals with measurements. We aren't going to do the experiments in order. We're going to jump around. So here are the objectives. You become acquainted with physical measurement techniques, both direct and indirect. Let me shut off the gas. To learn how to read and record data to the proper number of significant figures. To become familiar with the metric system. To practice unit conversions involving metric units. And then we go through a discussion section. I'm going to skip it. Let's go right to the data collection. And so here's the procedure. This is what we're going to do. Sometimes the procedures are quite complex, so you really need to work through these beforehand. Okay, procedure A, density of a liquid. Weigh a dry 50 milliliter graduated cylinder on the electronic balance. So I'm going to go grab an electronic balance from the corner and bring it over here. Let's get rid of these evaporating dishes. Everything's cooled down, so let's grab it in hand. Stir rod, crucible pan. Matches I'm going to throw in the garbage. Here's our electronic balance, one of them. This is a Scout Pro. I forgot the price on these. A couple $100 or more. So I'll set this down here, plug it in. Okay. All right, now I'm going to turn it on. This is the on-off button here. Let's turn it on. See what happens. Okay, let me move the camera so we can see it. So it just turned on, and when I turn it on, when we look at the readout here, it's reading out 0.00. Let's put the box of matches on there. That box of matches is weighing 5.71 grams. If I hit the on-off button again, it's the 0 button or the tare button. So if I push this, it'll 0 it with the box of matches. And so now that box of matches is reading 0. So if I throw something else, second box of matches on there, I can weigh it. And the tare function comes in handy because sometimes we don't want to weigh the container. We just want to weigh what's inside the container. So we'll 0 the container itself. Well, that container weighed 571, so it's negative 571 grams now. And so I'm going to just re-0 it by pushing this. And so now it's ready to go. We want to make sure it's level. If it's tilted, it's not going to give accurate readings. All right, so we need a dry 50 milliliter graduated cylinder. So here's my 50 milliliter graduate cylinder. It looks clean, fairly dry. This is a centigram balance. With a centigram balance can't detect fingerprints. A tenth of a milligram balance can detect fingerprints. And so if I'm using a very expensive $5,000 balance, I don't leave fingerprint residue here because it'll change the mass. But centigram, you can't tell the difference, so just weigh it. And so when I weigh this, okay, let's record it, 86.30 grams. So where do I record that? Well, I'm gonna record that into my lab notebook, you know, or your notebook. You shouldn't record it here because we wanna keep this clean, you know. It's nice to be able to keep this clean and not make it all messy because reports, you know, neatness counts. But your notebook, you don't really care. Throw it in your notebook, 86, empty graduated 50 milliliter cylinder, total mass, 86.30 grams. And so I need to record that here myself. In pencil. Let me grab a pencil. I'll be back. You're not supposed to record in pencil. You know why you're not supposed to record in pencil? Because pencil eventually fades compared to pen. So you're supposed to record all your data in ink. When you record all your data in ink, if you make a mistake, it creates a big mess. If we could record a raw data in pencil, then maybe it's okay to record it here. And so this is another reason why you want to record it into your lab notebook. So if you do make a mess, it's not going to be too bad. And so I had some Post-its I was going to put here, but I left them. I'll be right back. Oops. Well, you know, using Post-its is bad technique also, so I might as well do it. I just don't have a lab notebook, a proper lab notebook. A proper lab notebook would have a sewn binding. You know, I have it on my materials list. And so this is experiment 2 that we're doing, which is measurement. And so we could write that here. And then we'll just date it. Today's date is 7/23. 7/23? Yeah, 20. All right, and so we're doing part A, you know, density of a liquid. Actually, you know, the density of water, H2O, is what we're doing. That's the liquid. And so the density of water we're going to determine experimentally. And so what we're going to have is the mass, okay, mass of the 50 mil grad cylinder. And that was 86.30 grams. Let's say I make a mistake. If I make a mistake and I'm using ink, then you just cross it out with 1 or 2 lines. You don't scribble it out. That's poor technique. And then you rewrite it, 86.30. This is why you want to make all your mistakes in your lab notebook. You don't want to make all your mistakes on the report sheet, the final report sheet. And so make a mess of your lab notebook. Don't make a mess of your report sheet. Keep your report sheets nice and neat. Okay. It'll leave a more positive impression to the reader of the report sheet. Okay, what do we need to collect next? Masses should be recorded to the nearest, what we call centigram, 0.08x. You know, there are 100 centigrams in a gram. When using the electronic balance, add about 15 milliliters of distilled water from a squeeze bottle. So about 15 milliliters of distilled water. Now, we don't have any distilled water in this lab. We have what's called deionized water. And so I'm going to go over to the sink and find a decent squeeze bottle here. There's some water in the squeeze bottle, but I don't trust the last person to do this, because what if the last person put in tap water in here? You know, the last person just didn't know what they're doing. And so what I'm going to do is I'm going to dump this out here into the sink, and then I'm going to hit this is the DI water. Remember the DI water? I'm going to put some DI water in there, and then I'm going to rinse off whatever was in there with some DI. Squeeze it. When you squeeze it, you get water. I shouldn't put my finger out there. It could be acid. Rinse it off. That's probably, it's most likely DI water was in there. So maybe rinse it off. If you really don't trust it and looks dirty, rinse it off like 3 times or so. I'll just rinse it off once. Okay, this way I'm going to have a little supply. I'm going to have a little supply of DI water at my station, so I don't have to walk back and forth to the sink. I'll always have that here. Now they're asking us to add about 15 milliliters. And so it doesn't have to be exact. I mean, I'm just going to get close to the 15. And so I'm going to squeeze in some water in here until it hits 15, roughly. Now this is a problem. Since I was holding the video, I spilled some water on the pan. Do you see that? That's no good. I don't want any water on the pan, because that will lead to a huge error. And so what I need to do is I need to dry everything off here. Dry the grad cylinder. And this pan is actually removable. I'm going to dump the excess water into the sink and then dry off the pan. Yes. Otherwise, it's going to lead to an error about how much water I actually have in there. And then I'm going to just carefully align the pan back onto the balance here. There's a little tab. You see this little pin here goes right in the center here. There we go. And then, okay, I got rid of that there. Okay, now let's go back and resume my addition up to about 15 milliliters. I probably should watch. I was watching my computer screen. I wasn't trying to look at 15. Okay, it doesn't have to be exact, just about 15. That's what we want. But what we're going to do is we're going to measure how much water is in there. Okay, so I got about 15, but I need to know how much water did I just add. I know it's about 15, but I want to be as precise as possible, you know, and as accurate as possible in determining how much water I put in there. And so I need to measure that here. Okay, sometimes it's hard to see the meniscus. You see that? And so what some people do is they get a white piece of paper like this, and then they get a black pen, like this, and then just write a little black rectangle on here, like that. Okay, and what this does is it makes a meniscus stand out a little bit more. Let's see if I can get it to stand out a little bit more. Maybe. And so what we'll do is we'll read it. Okay, can you guys read that for me? The volume? I know it's not, is it focusing? Is it gonna focus for me? There it goes. What is that volume? Too blurry? Can you see it now? Not really? Well, okay, before I do that, let's take the mass. $100.72. So the next reading we're going to take is graduated plus 15 milliliters of water. So I'm going to do graduated plus 15 milliliters of water. And I got 100.72 grams. And then I need to get the volume of water. So do you see the mass here? Got that. Do you see this asterisk? Asterisk means calculated, and so I don't measure it. No asterisk means I have to measure it. So I need to measure the volume of water. This, I should be able to read to the nearest tenth of a milliliter. So let's try it now. Or if I can just... How about now? It's above 14, below 15. So if it's above 14, below 15, what are we going to measure it as? Let me see if I have a better black card that has different meniscus. This is also a meniscus reader here. This yellow collar here is a meniscus reader. So what I'm going to do is I'm going to line up the, this is what I'm going to do. I'm going to line up the yellow collar with the meniscus. Let's try that. Okay, I think I got it there. All right, so what I did was I lined up the bottom of this yellow collar with the bottom of the meniscus. And so let's read where the bottom of the yellow collar lines up. Can you see it? I was hoping I'd have better resolution. It wouldn't be so blurry. Is it too blurry still? All right, you're right, 14.5, Natasha has it right. 14, Diana, you have it right. 14.5 milliliters, that's what I got. And so over here, I have density, I have the mass of water here. I mean mass, total mass, this is the total mass. And then the next column is gonna be the mass of water. Mass of H2O. This is a calculated value, so little asterisk. And the next column over, I have the volume of water. And so there's no water here. There's no volume of water, but here we did have volume water. It was 14.5 milliliters was our volume of water. The last column here is the density of water. Density of water, but it's calculated, so there's a little asterisk there. All right, so now we can calculate the density. Okay, so we know that the mass of the grad cylinder plus the water is equal to 100.72. So if we take this and minus the mass of the grad cylinder, we'll just get the mass of water. So we'll take the difference of this to get the mass of water. And so 100, it's going to be, what is it going to be? I probably can do this in my head. It's going to be 14.42. So we have 14.42 grams. So if we take our 86.30 grams of empty grad cylinder, add 14.42 grams of water, we should come up with 100.72 grams of both grad cylinder plus 15 milliliters of water. Does that make sense? And so if we have 14.42 grams of water over 14.5 milliliters of water, then grams of water over milliliters of water is the density. So let's go ahead and calculate it here. And so, in other words, this was equal to 100.72 minus 86.30 grams. Total minus grams grad cylinder. That gives us grams of water. All right, so 14.42 divided by 14.5. What do we get from that? .42 divided by 14.5. Okay, I'm allowed 3 sig figs. And so this is equal to 14.42 grams of water divided by 14.5 milliliters of water, which is going to equal 0.9944. So 3 sig figs, because of the volume, I had 4 sig figs in the mass, grams per milliliter. And so the density I calculated is 0.994 sub 4, because I'm only allowed 3, I'll carry 1 extra. It's hard to take a picture. I don't know if I can take a picture of that. Let me see. What's this on off? You guys notice any difference? Let's see. Still take it. Something like that. Well, I'll take some pictures, try to take some pictures. Try cleaning that. Oh, I see, there's a light. Maybe the light helps. Okay, so that's kind of the pattern. Now let's do it a lot faster, because otherwise this is going to take too long to do the experiment. So what we're going to do is we're going to add another 15 milliliters of water. So we get about a total of 30 milliliters of water. And so what I'll do is add another 15, so I get about a total of 30 milliliters. Again, it need not be exact. If you overshoot or undershoot it, it's fine. Okay, that's about 30. All right, so we're going to get the mass first. So the mass is easy to read, 117.11. So when I take my grad cylinder here, and so this will be grad cylinder plus 30 mils of water, the total mass comes out to 117.11 grams. Okay, now I'm going to have to record the volume. So let me try to take a picture of this one. Although, you know, posting is just going to be time delayed. But it might be easier to read, huh? Wait. Okay. Oh, actually, this is better. You're right. This is better. Can you see that? Let me turn off the light. All right, what do you record that volume as? Well, it depends on where you're pinpointing the bottom of the meniscus. It looks like the bottom of the meniscus is just going a hair below the line. It's really hard to see, but it's going a hair below the line. And so this is 30, this is 31. So it looks like it's right below 31. I'm looking at this dark part right here. Here's the white line here. And so I'm looking at the bottom of this dark part. And so to me, it looks like 30.9. You're right, 30.9. And so I'm gonna go over here and say 30.9 milliliters of H2O. Then I'm gonna do the same thing. I have 117.11 total. So this is 117.11 grams total. Minus the cylinder weighs 86.30. 86.30. And so this is going to tell me how many grams total water I have in there, including the previous water. And so 117.11 minus 86.30. I left my calculator in the office. I have to use my phone. So 117.11 minus 86.30. 30.81. So I have 30.81 grams of water and 30.9 milliliters. And so the density, I can calculate the density. That's going to equal 30.81 grams of water over 30.9 grams, or not grams, milliliters of water. And so 30.81 divided by 30.9, 0.997. I'm going to go one more digit, 0.9970 grams per milliliter. Okay. That's the second one I got. Okay, now what we're going to do is add another 15, so we get a total of 45. Let's go ahead and do that here. Focus is still pretty bad. Well, it's blurry, but you can see the 45. All right, that's about 45. $131.19. And so the last entry here is grad cylinder plus 45 milliliters of water. Came out to 131.19 grams. I have a little error here. Do you see these little droplets of water? Those little droplets of water are not good. Those droplets of water, should be with the rest of the water. Otherwise, it's going to change the volume. And so let me try to wash those in to the rest, because we're weighing those little droplets. I'm weighing those little droplets, and I want them to contribute to the total volume. When I see droplets like this grad cylinder is dirty. This grad cylinder is dirty because that's called beads of water. When water beads like that, then the glass is dirty because water should wet the surface. So I didn't clean this. I should have cleaned this. I shouldn't have trusted it was clean. This grad cylinder is not clean. And so this is going to lead to a small error because it's not that much, those little beads of water aren't that much. But it's still something, so it's still leading to a little bit of error. And let me try to take a picture of this here, and then let's try to analyze the volume here. Now, this is kind of tricky here to see. This is not focusing so well, is that? Sorry. So what I'm looking at is I'm looking at the dark line right here. This is the bottom of the meniscus where I have the point of my pen. And so the bottom of the meniscus is going along like this, and it's hitting right on this line. You see how the bottom of the meniscus hits right on the line. So if the bottom of the meniscus is hitting right on the 45 line, that's the 45 line, what is the volume? This is 45, this is 46 actually. The next line is 46, this long line is 45. So if the bottom of the meniscus hits right on the 45 line, we call it 45.0. It's 45.0 because the next line is 46, 47, 48, all the way up to 50. And so it's 45.0. Over here, 45.0 milliliters. All right, first let's figure out how many grams 45 milliliters of water weighs. And so we'll take the total mass again, which is going to be 131.19 grams total, minus the mass of the grad cylinder empty, 8630 for the grad cylinder. And the difference will just be the water. So let's see what that comes out to. And so I've got 131.19 minus 86.3. Oops, 86.3. 4489. This is 4489 grams of just water. Okay, now let's calculate the density. The density over here is going to be equal to 44.89 grams of H2O per 45.0 milliliters of H2O. And so I'll take 44.89 divided by 45. Oops, how did that happen? 44.89 divided by 45, 0.9975. So I got 0.997, and then I'm going to carry one extra digit. The one extra digit I'm going to carry is a 5. I'm not going to round. I'm only allowed one rounding, so I'll leave it as 0.9975. And so now I just calculated 3 densities. Density of water should be the same, you know? But it's off a little bit because of experimental error, you say. What do we do next here? Now we've got to measure the temperature of the water. Okay, to measure the temperature of the water, let me go get a thermometer. Go get that. Thermometer is in the back of the lab, so I'll go back there and get it. Okay, so I have my thermometer here, and this bulb, we want to make sure the bulb of the thermometer is completely submerged. And typically we don't let the bulb touch the bottom, you know, especially if it's hot. But, you know, this isn't hot. And sometimes the glass and the water are at different temperatures. And so this is why we usually suspend it when we take our final reading here. This. But okay, we'll leave that in there and let it the temperature equilibrate, and then I'll take a picture of it. It's going to be hard because the reading is so low there. So I'm just going to take a picture of it and blow it up. I did it earlier. Okay, so I'm going to suspend it and then hold it so I can take a reading here. Okay, so what we're looking for is the blue. It's an alcohol thermometer. So we're looking at, now alcohol is going to be kind of like water, you know, but the meniscus is not really pronounced there. So we'll just go off the meniscus, I guess the top part of the meniscus is fine. What would you call that reading there? Is 10. To me, that reading, yeah, 19.0. I wouldn't call it 19 because it's right on the line. You know, we're allowed one guess, and the guess is 19.0. And so the temperature of the water, which is the next piece of data, temperature of water that we got to measure. And so I'll write it over here. Temperature of the H2O is 19, it's right on the line. So we got to add the 0.0, 19.0 degrees C. You know? And so when we look at something like this, it could be, you know, slightly above the line or slightly below the line or whatever, but that's right on it. All right, what's next? Okay, what's next is the average density. And so the average density is, we'll just add up these three densities and then divide by 3. And so let's do that over here. Average density equals, okay, I'm going to carry the extra digits here. It's 0.994 sub 4 plus 0.997 sub 0 plus 0.997 sub 5 divided by 3. The units are going to be the same for all these. I'll put the units over here, grams per milliliter, so I don't have to write it over and over again. And so let's go ahead and calculate the average of the 3 that we just determined experimentally. And so I'm going to take 0.994, 9944 plus 0.997 plus 0.9975 equals, divided by 3, equals 0.9963. And so the average density I calculated was 0.996 sub 3 grams per milliliter. That's the average. Let's see. All right, what's next? The next thing is we're going to get the accepted density. The accepted is the theoretical density, or, you know, it could be the experimental density as well, just accepted. And so this is the density of water table. The density of water table goes like this. At 4.0 degrees C, the density is right on 1. A temperature is lower than 4, it's less than 1. A temperature is greater than 4, it's less than 1. But it doesn't change much. And so what they do is, rather, you know, they have the density to 6 decimal places. Take a look here. There's 6 decimal places, but the first 3 decimal places don't change, really. And so the first 3 decimal places stay the same, so they don't rewrite it. So this next entry should be 999,874. This should be 999,881. So as long as the first 3 don't change, they don't bother writing it there. And so we'll do an example here. Let's say we want the density of water at 0.5 degrees. So 0.5 degrees, the density is 999,899. That's what it'd be. Now, when we hit like there, the density changes here. When we get to 999,999, the next entry, do you see that asterisk? That asterisk means use the next set of 3 initial digits. Well, the next set of 3 initial digits is 1000. So this density that's shown here is 1,000,000,000. And so that's at 3.8. At 3.9 degrees C, it's 1,000,000,000. And then at 4 degrees, 4.0 degrees, it's 1,000,000,000. And then at 4.1 degrees, it's 1,000,000,000. At 4.2, it's 1,000,000,000. Then when we get to 4.3, it says use the next set of 3 digits, first 3 digits. So the next set is 999. So we're back to 999. So this one is going to be 0.99999. That's what the asterisk means. And then once we're past the asterisk, then use the previous set, which is 999, 999,990, 999,988, etc. And so we're at 19.0. So here's a 19, and then we go to 0.0, which is the first column. And so at 19.0, we use the previous set of 3 digits. So that's 0.998435. And so the theoretical or the accepted density, what did they say? Accepted density here, we'll write it here. The accepted density is equal to 0.998435. 0.998435. That's to 6 sig figs, grams per milliliter. 6 sig figs. Okay, now we're going to do something called the percent error. The percent error, I wonder if there's a way to focus this thing. All right. Percent error is equal to the experimental minus the theoretical divided by the theoretical times 100%. And so in our experiment, we calculated an average density of 0.9963. Since this is a subtraction, I like to write it like this to keep the decimal places together. And so the theoretical is 0.998435. And so we're only allowed 3 decimal places according to sig fig rules. And so let's go ahead and do that calculation here. So I still have 0.9963 in my calculator, and then I'm just going to go minus 0.998435. And redo that, 0.998435. What? Let me redo that again, 0.998435 equals. Okay, so in the numerator here, I get negative 0.002135. I'm only allowed 1 digit though. 3 decimal places means only 1 digit. Divided by the theoretical. Okay, so maybe I'll do it over here. Keep that an arrow. And so I have 0.002. I'm allowed 3 decimal places. This is negative. And so I'm going to carry extras, but they aren't allowed, so I'm going to subscript them. Divided by the theoretical. The theoretical is 0.998435. That's 6 sig figs times 100%. And so what is my percent error? And so I'll take this number here, divided by my theoretical, 0.998435 times 100. And so my percent error comes out to negative 0.2. Now I'm only allowed 1 sig fig, but I'm going to carry some extras. So I'll just carry 1 extra. Negative 0.2 sub 1%, or about 0.2% error on the low side. So my density came out a little bit lower. That's what the negative means. I'm a little bit lower than theoretical. Some people put an absolute value, but chemists don't. Chemists want to know if they're a little bit lower or higher than the theoretical. We're a little bit lower we're 0.2% lower than the theoretical. And so that was our error. So about a 0.2% error based on what it should be. But that's okay because we had little droplets there. You know, there are some obvious errors that happened. If I clean this grad cylinder better, we might be able to get a little bit better density than that. Time is it? Is it break time? Okay. Okay, let's go on a break here. I got to go get the mass. So I'm going to stop, or I'm going to pause. Actually, I should just stop the recording. I'm going to pause the recording here, and then we'll go on break. We'll be back in a bit. Okay, we're back. So I'm back. We'll go ahead and get started again here. Okay, what's next? Okay, what's next is we're going to do the density of a solid. And so the first solid we're going to do is just a piece of copper metal. I have a piece of copper metal here. It's a little oxidized. You can tell there's a little bit of, you know, a little bit of discoloration there. And so just a little bit of oxidation. So we're just going to go ahead and do it. It's going to lead to a small error, but the amount of oxidation compared to how much copper there is, you know, there's not that much error. And so we'll do a sample of copper, and then we're going to get the mass of the metal cylinder. So this metal cylinder, we can just weigh directly on the balance. Let's see. But when I look at the balance is not reading 0. And so I better 0 it here. The 0 button. Okay, now it's 0. And so, oops, gotta be careful. I don't want to damage the balance. Okay, so 5690 is the mass of the copper cylinder. And so I need to record that data here. So this is going to be part B. Part B, we have multiple solids here. So part B is just density of a solid. That's right. And we're doing copper first. So we'll get the mass here. And that was 56.90. 56.90 gram, or 91. Seems to be fluctuating between 90 and 91. Sometimes that happens. Sometimes it's right on the borderline. I've got to make sure that this is really centered here. That's always annoying when it goes back and forth. See, it's right. It's like 56.905. And so little fluctuations will cause it to go up and down. And so there's going to be some uncertainty in that last digit there. Let's move it a little bit. Let me make sure it's zeroed again. I'm going to take this off. It looks like the zero's off a little bit. So I'm going to re-zero. It's probably when I dropped the mass on there, I probably damaged it. Do this. Maybe the pan is not. Sometimes the pan gets stuck. You know, I drop that mass. Okay, there's 0. I should gently place it on there. Keep an eye on it. Okay, now it looks stable. So maybe I damaged it a little bit. So we're just going to go 5690 grams. That's the mass of the copper. Okay, what do we need next? We need a volume of water. Well, the reason we need a volume of water is because we're going to measure this by water displacement. And the way we can measure the volume of that easily is by putting some water in a grad cylinder and completely submerging this underwater. And so I don't need this much water. Maybe 30 mils should be enough. So let me pour out. Oops, I poured out too much. And so let's pour in some more in here. I just need to make sure it's completely submerged. Probably 20 mils is fine. And so we're going to have to measure the volume of water before we add the cylinder to it. And so I'm going to take a picture of this and let's try to get a decent measurement. Again, these droplets here, you can see it. The droplets here on the walls is indicative of dirty glassware. We shouldn't have big droplets. So I tried to knock that big droplet back into the water here. And so let's take a picture and try to get a decent reading. See, I'm not sure if I got the right angle here. No, I didn't. Let me try it again. Okay, that's probably good. So let's take a look at this reading here. So what I'm looking at is 20 is here. See that? So it's between 20. It's hard to see because the white of the line and the white of the meniscus really make it hard to see. Here's 19, so it's between 19 and 20. Maybe I'll try to get some color in there, but I don't have 3 hands to do it, unfortunately. So I'm going to try to move this here like this. Try to get some background color in there. Let's pull this up. Actually, I don't need to hold the camera, do I? The webcam. I'm just going to hold this. Get some color behind the meniscus. That's still not going to be great, but let's see. All right. Oh, it's still hard to make out, but here's the white line for 20 that goes all the way across. Well, here's 15. And so you can kind of see, you know, just based on this, you know, the lines here. And so what does that look like to you? So there's 15's here. Oops, I probably can't see. 15's here, 16, 17, 18, 19. So it's between 19 and 20. And the 20 lines here. So what does that look like to you? The line is right about here. 19.5. Any others? Anybody else? 18. No, 18 would be down here, actually. Yeah, maybe I would say 19.3, actually. 19.2 or 19.3. It looks like less than halfway. I mean, look at the gap here. If you look at the gap here and then look at the gap here, it looks like a 19.2, doesn't it? Or 19.3. Four, 5. Yeah, maybe a 19.2 or 19. Okay, well, it looks like the consensus is 19.3. So let's go with a 19.3. And so volume, this is massive metal. This is the volume of water. And looks like, looks 19.3, I'll go with that. I might have went 19.2, but it's okay. Okay, what do we need next? Okay, then we need the volume of water and metal cylinder. Here. Volume of water and metal cylinder. And so what I need to do is I need to drop the metal cylinder into the cylinder, but it'll shatter the base. So what I'm going to do is I'm going to tilt this on its side, and then just kind of gently slide it in the bottom there. And so now the metal is completely submerged and the volume has gone up. And the volume is going to go up by the same amount as the volume of the metal itself. And so let me take a picture of that here. Let's see if we can get it. All right, this might be a little easier to read here. This is 25, this is 26. It's hard to see. I can see a lot better than on the screen. I think it's hard to see for you guys. Yeah, it looks like 20, well, it's almost 26. So 25.4 is a little bit, well, actually, I guess we're reading from the bottom of the meniscus, huh? So if we're reading from the bottom of the meniscus, if this is the, here's the bottom of the meniscus, it looks like right here. It looks like the bottom. And so, yeah, 25.4, or I would call it 25.5 myself. It looks like right in the center. You see, I'm not reading from the bottom of the white, I'm reading from the bottom of the meniscus. Let me see, did I do that on the last one? Meniscus looks quite a bit different here. You know, it's because I put the black background on there. In this case, I didn't put the black background on there. Maybe I should do it the same. Let me try to put the black background on there and take a picture of that. Like this. So I'm just using my battery charger. And take a picture again. Okay, now what we're looking, since I put a black background, it colored the meniscus, so it's a little bit easier to see, perhaps. Come on, focus this thing. Let me see. Okay, there. So the bottom of the meniscus is here. And so here's the 25, here's the 26. So to me, it looks like the bottom of the meniscus is halfway between 25 and 26. So I'd call it 25.5. Yeah, Priscilla, that's what I call it, 25.5. And so the next entry here is going to be volume of H2O plus metal cylinder. And I'm going to go with 25.5 milliliters there, Priscilla. Good. Okay, the rest are calculations. And so we need the volume of the metal cylinder itself. So the volume of the metal cylinder itself is, if we subtract these two volumes, we'll get just the metal cylinder. And so the volume, this is a calculation, so we can put an asterisk there. Metal cylinder equals 25.5 minus 19.3. Background noise. Let me see. Okay, yeah, 6.2. Okay, so that metal cylinder is 6.2 milliliters in volume. The next calculation we're going to do is the density. So if we have the mass and the volume, we can calculate the density. The density, our book uses capital D, most books use lowercase d, of the copper is going to equal the mass over the volume. The mass is 56.90 grams. The volume is 6.2 milliliters. Unfortunately, we're only going to get 2 sig figs from this because of the volume. If we use, maybe we should have used a 10 milliliter. Let's put it in 10 milliliter. me check something real quick. No, the metal cylinder is too big. We could get better precision out of a 10 milliliter. That is, we could get 4 sig or 3 sig figs probably, or 3 sig figs, but it's too big. So we're stuck with 2 sig figs. And so it's 56.90. 56.9 divided by 6.2, 9.177. So 9.17 grams per milliliter, or 9.2 grams per milliliter. That's what we get here. All right. The accepted density is 8.96 grams per milliliter. And so this would be the theoretical or the accepted density. It's a given. Accepted is 8.96. And we're going to calculate a percent error. The accepted we call the theoretical. And the percent error is going to be the experimental, again, minus the theoretical, divided by the theoretical, times 100%. Experimental, we got 9.177. Theoretical is 8.96, divided by the theoretical, 8.96, times 100%. And so let's see what we get here. Okay, the percent error here is much larger at 2.34%. And so doing the top here, how many sig figs are we allowed? And so normally I would do it like this, 9.17 minus 8.96. We're allowed 1 decimal place in this calculation, so I should have done that first. So 9.17 minus 8.96, it's 0.21. So we're only allowed 1 sig fig, and then we divide it by 8.96, etc. And so this is going to come out to 2.3% or 2% error. 2% error is getting a little bigger. You know, our last error was 0.2. And so what we could always do is we could always redo the calculation, but there's going to be some error, you know, some error because of the oxidation coating on there, and some errors in reading this and elsewhere. But that's the error we got. It would be nice to repeat it, but we don't necessarily have enough time to repeat it. And so what we're going to do is we're going to do an unknown. Now, the unknown is going to have an unknown number. Here's some unknown metals. When I look at the metals here, some of these I already know. Like this is lead. I don't want to touch that with my fingers. I just prefer not to touch. This looks like aluminum. That's probably okay to touch. Let's go ahead and touch that. I'm guessing this is aluminum. It's pretty light. And so let's try to measure the density of this. So the first thing we need is the unknown number, okay? So we'll write this down. This is unknown number 6. And so whenever you're given an unknown, you always have to write the unknown number. Otherwise, we have no idea what unknown you actually got. So I'm gonna write unknown number 6 up here. And then we're going to do the same thing. And so let me dump out the water out of this. Get rid of the I don't have to dry my graduated cylinder. You know, it's okay if it's wet. We got paper towels. We have paper towels on the end of the bench here. So I got paper towel. But again, I don't need to dry this. And so I'm going to take my chunk of aluminum, number 6, and let's go ahead and weigh this. Oops, let's make sure it's tared. There's 0. It's not. 0. Put that on there. And then number 6, 3511. Looks stable. And so we'll go over here. The mass of the metal is 35.11 grams. And then we need the volume of water. And so I need enough water to submerge this. So let's put that next there and just make sure I have enough water to completely submerge my metal. Okay, that should do it. And let's go ahead and take the reading off this. And I'll try to use my meniscus reader. Just anything, you know, could be just a piece of paper with a black line on it. Could help. So I'm just using my charger here, which is black. And so it should color the meniscus. A little bit black as well. And so let's see, we lit that up a little bit. Okay, there we go. Get this focused. Maybe I got it because I was moving my hand quite a lot. Yeah, this is good enough. All right, let's take this reading here. Okay, so what I'm doing here is I'm holding the black object a little bit below the meniscus, so it looks black. The meniscus looks black here. And we can see the bottom of the meniscus. So we'll go off with the bottom of the meniscus here. I can see the white line here. And so this is 15, this is 16. So it's between 15 and 16. And it looks like it's more than halfway. 15.8. Let's get another reading. Yes? Anybody else? Yeah, 15.8 looks okay. 15.7. You know, me, I might go with 15.7, but 15.7. Anybody else? Could be a tie. We'll just go with whoever wins. So we got 2 15. Oh, okay, 3 15.7s, 2 15.8s. Anybody else? All right. Well, looks like nobody else. So we'll just go with 15.7. It doesn't really, you know, whatever you do, you just try to be consistent. That's all. Okay. Now I'm going to put the metal in here without breaking the bottom of this. So we'll tilt this and then just gently let it slide down. There. Okay, now it's submerged. All right, and so we're going to take another measurement here. And so, oops, sorry. So I'm going to try to use this to mark the meniscus. So I'm going to raise this up. The other thing is we got to make sure we don't have parallax. Parallax is when you're reading it too high or too low, you know. Okay, so what I see here, I see the 25 is this long line here. A little bit of parallax. Do you see? I see the back of it. And so I'm a little bit too high, but maybe this is okay here. So there's 25, 26, 27, 27, and then here's the 28. So it's between 27 and 28. So we got 27.6, 27.6. Anybody else? 27.6. 27.5, 27.5. Okay, we got another tie. We need a tiebreaker here. 27.6. Okay, it looks like 27.6. I probably would have said 27.5 myself. You know, but whatever you do, you be consistent, because it kind of looks like the bottom of this black line here is midway between these two white lines. That's what it looks like to me. And so it looks like a 27.5, but we're going to go with 27.6. So consistency is important. And so whatever way you read it the same way. Okay, now the rest are calculations. So now we can calculate the volume of the metal. The volume of the metal is 27.6 minus 15.7. And so I guess you could do that in your head, or you can do it on a calculator. 27.6 minus 15.7. 15.7. 11.9 milliliters. So that chunk of metal weight, has a volume of 11.9 milliliters of metal, volume of the metal cylinder. Okay, the next one is the density. So we'll just take the mass divided by the volume. The mass is 3511 grams divided by a volume of 11.9 milliliters. This one is going to give us a density of 3 sig figs. The previous one only gave us 2 sig figs because the volume of the copper cylinder was less than 10. So we'll get 3 sig figs at least here. And so I'll do 35.11 divided by 11.9 was 2.950. And so 2.95 is 3 sig figs, and then we'll carry an extra grams per milliliter. Well, if that's aluminum, we're a little off. You know, aluminum is 2.7, but it might not be. So we'll see here. Okay, that's all we're going to do here, because we don't know what the accepted density is. It's an unknown. And so it could be some aluminum alloy, something. And the percent error, we're going to leave blank because we can't calculate that either. Yeah, so let's move on. That one I'll come back to later. So we'll leave those last two blank. Part C, I'm going to skip that for right now and go to part D. Part D is the indirect determination of the mass and volume of 1 drop of water. And so what do we need for this? Now, when the time, you know, we keep track of time in lab, and if time becomes more and more pressing, what we do is we just make sure we collect the data, the raw data. The ones with an asterisk, we can do at home. These are calculations. And so we just got to make sure we got the data and do the calculations at home. And so I'm going to do this here, the mass of a dry grad cylinder. So I'm jumping to part D. So we just finished part B. I'm going to go to part D here. And so this is the mass and volume of the drop. A drop of water. Drop of water. You can read that. And so we need the mass of a dry grad cylinder. So the only dry grad cylinder I have is my 10 milliliter. And so that's fine. I'm going to use the 10 milliliter. Otherwise, I have to dry my 50 milliliter. I'm not going to do. I come over here to the balance, make sure it's 0. It is, and then weigh this. And so it's 37.46. It's like stable at 37.46. So go back over here, 37.46 grams. Okay, the next thing is I'm going to add some drops of water to that. And so I'm going to leave the grad cylinder on the balance here, and then just add some drops of water. Now, using a spray bottle is too hard to get drops. I usually get streams of water using a spray bottle. And so I'm going to get a medicine dropper and then drop it in there. I'm supposed to add 60 drops of water, I think. But I don't want to put the medicine dropper into the bottle because that'll contaminate the water here. And so what I'm going to do is pour this into a small beaker. That way I avoid contaminating my source. And this, I can toss this after I'm done with it. And so I'm going to count 60 drops. All right. This dropper is not working. I have another dropper here. This dropper is working. Okay, ready? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60. All right, so we got 60 drops of water in there. And so the drops of water added, we'll write here 60 drops of H2O added. Okay, then we want the mass of the graduated cylinder in the water. The mass of the graduated cylinder in water is 40.5. Let's see if it's stable. 40.51. So mass of cylinder plus water, 40.51 grams. Okay, now we need the volume of the water. Okay, so I'm gonna get the volume of the water here. Okay, now this is a different grad cylinder, you know, different precision. This is a higher precision cylinder, this little one here, than the big one. And so we're gonna read it differently than we just read the last one. And so let me take a picture of this measurement here. Let's see, get that. So I'm gonna just use this to kind of darken the meniscus. I could also use something like this to darken the meniscus. I'll use this. Get this up here, easier probably, till the meniscus turns dark. Actually, it's kind of, move this closer because it's so low. So low that hold the foam down more. All right, hopefully that got it. So let's take a look here. It's hard to see. Hard to see. Well, I see the meniscus easily. I just don't see the line so easily. I have to do that one more time. How much time do we have? Okay. So let me take one more picture of this. I'm gonna make the card smaller so it's easier to hold. hold this here. I guess you can't see much of my arms there. Let's try to darken the meniscus there. Yeah. All right, let's see if this one was any better. Well, at least I could see the line a little bit better, but I have some parallax. I'm not holding it. Well, let me show you what I'm worried about here. Oops. So I have to use one or the other. The thing I'm worried about here is this. If I look at the 3 mark, this line, the long line's a 3, I see the back of it. Since I see the back of it, that means I'm holding it, I'm looking up at it at an angle, you know. If I look at the 2, I don't see the back. Do you see that? And so this is perfectly perpendicular to the 2, but it's looking up at it at the 3. And so this is going to give me an incorrect reading. Let me look at the previous one. Maybe we'll just have to go with this. So hard to see though, but the 3's here, the 3.1's here. So it's between 3 and 3.1. 3 and 3.1. So what would you say? Boy, that's hard to see. Well, we got 2, so let's just go with this and then see. What would you say it's here? This is the 3. Let's see if I can get this better focus. This is 3.1. 3.1 is here. And so it's between 3 and 3.1. Do you see it? And so I'd say it's a 3.0 something. I'd say it's here, so I'd say it's a 3.02. I wouldn't say 3.05 would be midway. This is less than midway. So I would say it's like a 302, maybe, but I'm also tilted at a little bit of an angle, maybe. And so let's look at the previous one here and see if this one gives us a little bit better picture. And so over here, I have the 3 line, which is here. It's barely visible. Might not be able to see it so well, but this is 3. And then this is 3.1. So 3 and 3.1. And so it looks like 3.01, 3.02, 3.03 is in that range. So I see a 303, 301. So let's go with a 302, maybe. There. Those pictures weren't the best, but I'd take some more, but I accidentally spilled it. And so I don't want to count the drops again. So we're going to go with that. So let's say 3.02. We'll split the difference between yours. And so this will be the volume of H2O. All right, that's what we need here for the raw data. And so we're done with the raw data here. We could do the calculations later. So let's do the calculations later. And let's go to part C here. Part C is the indirect determination. And so here, I'll leave some room for the calculations. We're going to go part C. And so first, I'm going to get a packet of paper. And so let me go grab it. I'll be right back. Okay, so I have a packet of paper here, It's unknown number 9, green. So we'll put that on here. It's number 9 green is the color of the packet, we'll just say. So number 9 green is a part C. And then mass of 250 sheets plus plastic cover. Now the mass for this paper this is too much weight for our little balance here. And so what we're going to do is we're going to put it on triple beam balance. So I'll just set it here on the pan here. And then what I have to do is I have to balance out the mass here, over here. And so what I'm going to do is I'm going to just dial it maxed out, all the weights here. When I throw all the weights here on the right, it's still not heavy enough. You see that? This is still too heavy. So I have 1,000 kilograms. This is a 1 kilogram mass here. I'm going to hang the 1 kilogram mass on the end here. Oh, now I have too much weight. You see here, I got too much weight on the right side. And so let's take the big mass and dial it back. Actually, this is the big one here, to 400, and to 300, and then to 200, and then to 100, and to 0. At 0, it's too little. You see, it's now gone that way. And so let's go back to 100, and then I'm going to dial this one down, the next one. 70, 60, 50, 40, 30. So 30, okay, let's go back to 40 here. 40 is a little bit too heavy, and then I'll dial this one back, the little one, the grams. Okay, still not quite. Let's go back to 30 and then dial the grams up. This is looking good. And so what I'm looking for are the two lines to match up. And it looks like they're pretty well matched there, maybe. Can you see? Just maybe just a hair. Okay, there. And so how much mass do I have? I have 1,000 grams plus 100 plus 30 plus 7. Okay, when I look at this, I see 7.55, looks like. Here, maybe I need to take a picture of this. How much time do we have now? 6:03. Fortunately, we don't have enough time. So when you look at that, what does it look like to you? We have 7 over here, and we have 8 over here, and 7.5 in the middle here. And so it looks like it's just past 7.5. Yeah, yeah, 7.55 looks right. And so we'll go with 7.55. And so the mass, let's write it over here. The mass is going to be 1,000 plus 100 plus 30 plus 7.55 grams. And so this is going to be 1,137.55 grams. That's what we're going to get. Okay, well, it looks like we're out of time. So what we're going to have to do is we're just going to have to finish this with the next lab. The next lab is not going to be on Monday. I'm going to do the next lab on Thursday. And so I posted that note on Piazza. And so we'll come back to lab on Thursday. We'll finish this lab, and then we'll do the other labs. Okay, I'll try to upload the pictures of the readings. Okay. All right. Well, anyway, that's it. I'll get your exams back to you tomorrow, and then we'll see you guys on Monday. Monday will just be a lecture day. All right. Have a nice weekend. Let me see. Do we have an exam next week? Yes, okay. Well, the exam's going to just cover, I'll talk about it on Monday, I guess. It'll be the same kind of deal. We'll talk about the exam on Monday. Take home. Okay. Great. Thanks. See you Monday.